the final section in Chapter 8. Section 8.3 discusses how to put things in simplest radical form. Now let's talk first about operations with radicals. If we look at, for instance, two things multiplied together within a radical, we can split those up into their respective pieces and take the root of each. This can work both ways. So sometimes we have a perfect square and we want to factor that out and take its root and then have the remainder of what is not a perfect square left under the radical. Likewise, it's possible we have two radicals multiplied together, and as long as they have the same index, that number here n, so square roots can multiply with square roots, cube roots can multiply with cube roots, so forth and so on. As long as that's the case, then we can multiply what's inside together, and possibly they create a perfect square, which will come out to be a nice number. Similar to multiplication, we can do this with division. We can split this up into separate radicals, one in the numerator, one in the denominator. Again, we always want to make sure that we are not taking the radical of a negative number, and we want to make sure when we're dealing with fractions that we do not cause the denominator to be 0. So those are our issues there. Likewise, this is a nice rule when we have a radical within a radical. We can multiply those two indices or the index numbers together. So this is the same thing, for instance, if you had a power to a power. So for instance, if we had a to the 1/nth to the 1mth, this would be a to the 1 over n times 1 over m, which is a to the 1 over nm, which, as we know, gets us back to that radical, the root of mn or nm. It doesn't matter which order they're in because it's multiplication. So let's take a look at some examples. These first few examples here are going to play with Rule 1. If we look at 48, we say, okay, can we figure out the largest perfect square that divides evenly into 48? So we know that 4 would divide into 48. 9 does not. 16 does, so that's good. 25, we're starting to get too big because we're already more than half of this, so that's not going to work. So let's look at splitting this up into 16 times 3, that's what 48 is, and then we can use Rule 1 here. We can split this up into these two radicals, the square root of 16 times the square root of 3, and since the square root of 16 is a perfect square, we write that as 4. Again, we get rid of the radical, we don't leave it there, but we do leave it with the 3 because we did not perform that operation. So we've got 4 square root of 3 as our simplified answer. We can do this as well for powers of variables. Again, if you look at this, 18 is not a perfect square. 4 would be the first one, obviously fits in. 4 would be the next perfect square. That does not divide evenly. 9, however, does, and that is half. So that's as far as we're going to go. Once you get to the halfway point, it's not worth checking any higher because you would have to multiply by 2, which is the smallest possible number if this number isn't prime that we can multiply by. So this ends up being the square root of 9 times the square root of 2. And then if we look at the square root of x cubed and the square root of y to the 8th. So we said the square root of 9 is 3. Square root of 2 we can't simplify any further. The square root of x cubed, we can pull 2 of these out. We could rewrite this as the square root of x squared times the square root of x if you wanted to, or you could just say I'm going to take out as many multiples of 2 out of this. So I'm going to have an x, because the square root of x squared, and then I'm going to be left with an x, because again, if you pulled that back in, you'd have to square it and you'd get x cubed. Similarly here, y to the 8th, that is an even number, so when we take the square root of y to the 8th, we end up with y to the 4th. Again, you can kind of think about this. If you rewrite it as the fractional exponent, you would have 8 halves, which is y to the 4th. So similarly here, you could have written this as x to the 3 halves, which if you think about that as a fraction, you want to take x to the 1 and x to the 1/2, split those up, and that's what you end up with here. You've got an x and you've got an x to the 1/2. Let's take a look at some other examples here. So in this case, we've got a fourth root and a fourth root. And if you look here, you can simplify the y to the fifth and the y to the sixth, but you can't simplify the 25. This is where Rule 1 works better going backwards. If we multiply these together, again, we have the same index 4 here, so we can bring these together. We have 25 y to the fifth times 25 y to the sixth, so we can simplify. We've got the fourth root. 25 times 25 is 625, and then we have a y to the 11th. When we add those exponents 5 and 6, we can take the fourth root of 625. 625 is a perfect fourth, so we get 5. And again, if we look at multiples of 4 that fit into 11, we end up with 2 of them, so we would have y squared. That would get us 8, and we'd have a remainder of 3. So we'd still have this fourth root of y to the third. That's another way to look at it. You can say 11 divided by 4 is going to give me 2, remainder 3. So the 2 comes outside, the remainder stays inside the root, and we make sure we have that index of 4. One further example, this works for rule number 3. If we look at a radical within a radical, so we've got a cube root within a square root, we can assume that that's a 2 because it's a square root. We can simply multiply these indices based on our rule there. So we now have the 6th root of x to the 13th, y to the 5th, and z to the 8th. And again, if we use our remainder rule, we say, okay, 13 divided by 6, that's 2. So we pull out an x squared. We're left with 1x still inside. So again, 13 divided by 6 is 2, remainder 1. Y to the 5th does not divide in. We've just got a remainder of 5. And z to the 8th, 8 divided by 6 is 1, remainder 2. And so that's how we end up with that answer. X squared times z times the 6th root of x, y to the 5th, z squared. So I want you to pause the video at this point and try example 25. So for the first part of example 25, you should have been able to pull out a cube root of 8, which is 2, and then x to the 6th, the cube root of that is x squared, and the y to the 8th, again, if you do 8 divided by 3, you get 2, remainder 2. And again, with the 24, you would have had 8 times 3, so that 3 is going to stay in the cube root, and then there's your remainder 2, the y squared, that's going to remain there. For the second part, again, if you multiply these together, it works out a bit better. If you were to simplify the square root of 32, you end up with 4 root 2, and then you'd have to multiply by the other root 2, and it gets a little messy. Whereas if you just multiply the 32 and the 2, you get 64. Square root of 64 is 8, and the square root of 8 to the 6th is a cubed. So finally, we want to look at writing radicals in their simplest form. And there are some rules that go along with this. First of all, a radical contains no factors of power that is greater than or equal to the index n. So that was what we were doing up above. There are no fractions contained within a radical. There are no radicals in the denominator of a fraction, and this is what we call rationalizing the denominator. When we get rid of that. And finally, the index of the radical is as small as possible. So let's take a look at a few examples here. We want to just start off simple, the cube root of 108. 108 is not a perfect cube, so we look at what divides evenly into 108. Again, when we talk about this, we're always talking about dividing, because we need to look at factors. First cube is 1, obviously that fits in. The next cube is 8. 108 divided by 8 is not a whole number. So we move up to the next perfect cube, which is 27, and that will fit in. That will end up giving us 27 times 4. So we end up with the cube root of 27 times the cube root of 4. Cube root of 27 is 3, and then we are left with the cube root of 4. Again, cube root of 4 does not simplify any further. And I want to point out something here. Always make sure that you're careful here when you're writing these, especially when you have an index other than 2. Just to make sure that this does not look like an exponent on 3. You can either put some space here between them, or you can put a times in between, just so that you make sure that the 3 is the index on the radical and not the exponent on the 3. So let's look at another example. We've got another cube root here of 375. Again, 375 is not a perfect cube, but 125, which is a perfect cube, fits into it. Also, we luck out in this case, a negative under a cube root is possible because negative 1 cubed is negative 1. So we can look at the cube root of negative 125, and then that would leave us with the cube root of 3. And then again, we can look at our x to the 4th, our y to the 6th, and our z to the 8th. So we can either keep them separate or put them all back together in the end, which is what we're going to do. So we've got the cube root of negative 125 is negative 5. Cube root of radical 3 is going to stay, so we'll kind of write that over here because we'll have some other things remaining in the root. X to the 4th, when we take the cube root, again, 4 divided by 3 is going to give us 1, remainder 1. Y to the 6th, and we take the cube root, that's just going to give us y squared. And z to the 8th, the cube root of that, again, and this is where we want to make sure that we have enough room, so I'm going to move this over. We have z, 8 divided by 3 is 2, remainder 2. So we end up with negative 5x y squared z squared times the cube root of 3x z squared. So I want you to pause the video here and try the first part of example 27. So for this one, you should have ended up with 9b cubed. Again, you've got b to the 9th in the cube root. 9 divided by 3 is 3. C to the 4th, because 14 divided by 3 would be 4, remainder 2. And then left under the radicals, since 729 is a perfect cube, it is the cube of 9. Then we're left with our a squared that didn't simplify, the b ended up coming out, and then we had a c squared as our remainder. Now let's look at rationalizing denominators. In this case, we want to start off first by simplifying these radicals. So we've got the square root of 8 over the square root of 27. The square root of 8 can be thought of as the square root of 4 times the square root of 2. And the square root of 27 can be thought of as the square root of 9 times the square root of 3. Or when we simplify 2 and we have that root 2. Same thing in the denominator here, we have 3 root 3. So what we want to do when we rationalize the denominator is we want to multiply by 1. So we are going to multiply by the radical piece of the denominator here. So we are going to multiply by root 3 over root 3. And if you remember from the last section, when you multiply a radical by itself, you end up with what's inside. So in this case, we end up with 2. We're going to use that rule from up above that says we can multiply what's inside the radicals. So we're going to end up with the square root of 6 over 3 times 3, because we've got that square root of 3 times itself. And so we end up with 2 square root of 6 over 9. Now I don't want to see anybody trying to simplify this 6 and the 9. This 6 is inside a square root, so it is protected, if you want to say. We can't factor anything out to make it simpler, so it cannot divide by that 9 there. A little bit simpler example is just to look at 1 over the square root of 7. In this case, we would just multiply by the square root of 7 over the square root of 7. Again, we're multiplying by 1, and you end up with the square root of 7. Square root of 7 squared is 7, so that's our fraction, the square root of 7 over 7. Sometimes we want to simplify. Again, we don't like radicals in the denominator, so in this case, we only need to multiply by what's going to get us to this index. So in this case, we could multiply by the 5th root of x squared, because the squared would get us to 5 over the 5th root of x squared. So again, what I'm trying to do is look at this number here, this 3, and say, what do I need to get to 5? In this case, I only need 2, so I'm not going to multiply by the exact same thing. If I multiply by the exact same thing in this case, I end up with the 5th root of x to the 6th, which still leaves me with a radical in the denominator. So in this case, I end up with the 5th root of x squared over, like I said, we got the 5th root. It ends up being of x to the 5th, which is nice, because then that ends up being x in our denominator. So our final answer ends up being the 5th root of x squared all over x. A few more examples here. If we want to take the square root of 3x over the square root of 2y, again, we're going to use that second rule that we had up above. We're going to split this up into the square root of 3x over the square root of 2y, so we're splitting that fraction up. And now, since we have a square root, this is relatively simple to multiply by 1, so we're going to multiply by the square root of 2y over the square root of 2y. So we have 3 times 2 is 6, so we have the square root of 6 xy over square root of 2y times the square root of 2y just gives us 2y in the denominator. So our numerator in this case is the square root of 6xy. Denominator is a non-radical function, 2y. We have one final example here in this type of problem, and that is to have some multiplication of radicals. And when we have that, sometimes it is just easier to combine things. The problem here is that we have different indices. We have a cube root, we have a square root, we have a 4th root. So you have a couple of options. One option is to try to simplify things, bring things out first. Another option is to rewrite them with their fractional exponents, combine like terms, and then write it as one big radical. So since this is multiplication, we can do this. If it was addition or subtraction like we have down here, that will not work. It only works for multiplication and division. So what I'm going to do is rewrite each of these with their fractional exponents that we discussed in the previous section. We've got a to the 4/3, b to the 2/3, and we are multiplying that by a to the 4/2, which we can just reduce to 2, and a to the 3/4, and b to the 4/4, which is just b. So now we're going to put like terms together. So we have a to the 4/3. Since we're multiplying, we're going to add the exponents. So a to the 4/3 plus 2 plus 3/4, and b to the 2/3 plus 1. So again, practice with our fractions here. We'll practice our fraction addition over here on the side. 4/3 plus 2 plus 3/4. Well, our common denominator in this case is 12. We're going to need to multiply by 4/4 for our first fraction, by 12/12 for our second fraction, and by 3/3 for our third fraction. And this would give us 16 plus 24, which is 40, plus 9, which is 49/12. So we end up with a to the 49/12. B is a little simpler. This just ends up being b to the 5/3. To put these back into the same radical, we still need to keep the same denominator. So we've got a to the 49/12 times b. This is pretty easy. Just multiply by 4/4. You end up with 20/12. And so again, we do our simplification. 49 divided by 12 would give us 4. And then our remainder 1 would go inside the 12th root. For b here, we have 20 divided by 12, which would give us 1, and then we would have a remainder of 8. So either of these answers would work here. Got our a to the 49/12, b to the 5/3, or if you want to write it in radical notation, we have this answer here.
Now on this final example, we're going to look at addition of radical terms. What we always want to do first is to simplify any radicals just like we did before. So in this case, when we look at the square root of 8x cubed, we're going to have that 5 is going to come along. And then we've got the square root of 8, which is 2, root 2. And then we've got x cubed, so that's going to be an x, and an x stays under the radical. We've got a 7x here. When we simplify the square root of 50, that is going to end up being 5. And then root 2 stays and x stays in because there's no power on x. And finally, we got 9x, and the square root of 75 gives us another 5. A 3 would stay inside the radical, and then the square root of x to the 7th is going to give us an x cubed, and an x is going to stay behind inside the radical. So when we simplify here, we've got 5 times 2x gives us 10x, root 2x, plus 7x times 5 is 35x, times root 2x, and finally we have the negative 9x times 5x to the 3rd, so we get negative 45x to the 4th, and a square root of 3x. Now these two terms both have a 2x in common, so we can factor that out, and we are left with a 10x plus a 35x. And then this square root of 3x doesn't belong, so it's just going to stay minus 45x to the 4th, square root of 3x. Finally, 10x and 35x can be added together, so we've got the square root of 2x. We'll move that 45x to the front, and then we've got a minus 45x to the 4th and a square root of 3x. One last thing you could do if you wanted to, depending on what answer you're looking for, it might be that you want to leave these terms separate, and that's fine. If instead you want to kind of try to factor as much as possible, and this is where you have to be careful what the problem is looking for, it is possible, since these both have a 45x in them, that we can factor out our 45x. In that case, we'd be left with a square root of 2x minus an x cubed square root of 3x. Again, either of these answers is acceptable. It just depends on what the problem is asking for. So this concludes the video for lesson 8.3. Please go online and complete your homework now for that section.